So now we're on to the cardiac output, which is another interesting topic. Cardiac output is defined by the amount of blood the heart pumps through the cardiovascular system in 30 seconds. So as you can see here, yeah, you get cardiac output. You get this value you can see from the figure by multiplying the heart rate and the stroke volume, and as you can see, it magically sort of cancels itself out, and your cardiac output is either in liters per minute or milliliters per minute. It just depends on who's calculating and what they're typically looking for. So the normal cardiac output is about 4.7 liters per minute at rest. And some of the reasons why we need this is because a low output means that your heart's not pumping enough blood, but it can signal heart failure. Heart failure. And, this can also, a low input can also happen from, I'm missing a couple letters in here, from severe blood loss, either from a surgery or something like that, or even an injury. So sepsis is also another cause of low output because your body's trying to overwork to fight these infections. So it can reduce blood flow to your organs, your limbs, and then it can cause severe irreversible damage to those organs. So it's pretty important to know this right away. So high output is completely different. So it can occur when you're lacking oxygen carrying red blood cells. It's called anemia. So this results in your heart pumping too much blood and super active, rapid rate. So using calculus is a little bit simpler than the blood flow portion. So typically for the calculus aspect of this, we use a dye to simplify the mathematics. So the dye is injected through the right atrium, goes around the body, back through the heart, and goes out through the aorta. Probe measures the concentration of dye leaving the heart within a specific equally spaced interval known as 0 to t, as I said right here. The subintervals of delta t are all of equal length. I think that's one of the most important parts to remember in whatever sort of integral that we have been doing so far, is that the subintervals, when they're present, that they have to be of the same length or else it's not going to work. So the amount of dye flowing past the aorta is measured in the interval t equals t I minus 1 to t I. So in terms of this this situation, the CT counts for the concentration of dye at time t. The intervals are called delta t. F is the flow rate, and what you get is another equation, another Riemann sum. So here is your Riemann sum. What you can do is you can take out this F because it is a constant, so you can take it out of this Riemann sum. And you notice right here at the top, the A is left empty, and it is not because I forgot about it. It's just because that it comes in another equation a little bit later. So one of the reasons why this Riemann sum looks like this, and it does not have the T equals Ti and things like that, is because we assume that the delta T is very small, so the concentration of blood at T equals Ti is the same as T equals Ti minus 1. So that's why that we just put it into as delta T. This Riemann sum allows us to calculate the total amount of dye present, and as you can see, there's going to be another limit. As you saw my handwriting, there is a new limit coming. So the limit looks like this. Remember, I took out this the flow rate, and I took it out to put it in front of the integral sign. Since you cannot plug in and repeat the infinity at the top of your, as one of the bounds on your integral, that's why you make the limit of t goes towards infinity, and what you're left with is c of t, which is the concentration of that time t dt. This will give you that A I was telling you about, which is the amount of dye, which is typically known, so that's one of the values that we can put in a second. So since A is typically a value that will be given to us, and we can figure out the integral by ourselves. What this leaves us to, it keeps moving. What this leaves us is this f. So then you would transform the equation of f equals the amount of die that we're given over your integral of 0 to t, c of t dt. So typically, we figure out the integral and then we divide the amount that we're given by the integral number that we get, and it would give us our flow. So like I said, this is a little bit easier than the blood flow aspect. So cardiac output is a little bit simpler. The integral is not as lengthy and as complicated to get to. So here we're going to do 2 quick examples, and hopefully it'll help you out. So welcome to the example. This is a mock example of just like a step-by-step mechanism, methodology, because this is typically what I like to do. I think it's much simpler than using a specific step-by-step process. So your step 1 is determining your variables. So like your A, your C of t, your delta t. Your step 2 is setting up everything, so including your integral into, whoops, that's not how you spell integral, and the function. Your step 3 is your evaluation of the integral. So this is one of the nice things, because there are technically 2 ways that this can be done. So one of the ways is you use Simpson's method, and that's if you're given a table of values. Simpsons, and remember that's delta x over 3 f of x0 plus 4 of x1 plus 2 f of x2 and so on. Or the other way is if you're not given a table, obviously, then you just take the regular integral. So step 4 is putting integral in your equation. So whatever you get here, you put in equation, and your step 5 is, remember, to your appropriate units. I think that's something that we'll have to worry about now, because it's not something that we discussed really throughout the semester. There weren't that many sections where we had to worry about units. So anyways, if you're interested, you can go to page 479. There's an example in the book where we are given a data table, so that's kind of nice. So if you read the problem, a 4 milligram bolus of dye is injected into the right atrium. The concentration of the dye in milligrams per milliliter is measured in the aorta at 1 second intervals, as shown in this chart. So as you can see, I drew out the chart in a couple seconds, and then the question asks for the estimation of the cardiac output. So from the problem, your A is 5, your delta T is 1 since you're trying to measure per second, and then the total time period, the capital T, is 10 seconds. Put the units here. As you can see, the integral sets up 10 to 0, C of t dt equals 1/3, and then your Simpson's method. So remember, Simpson's method is f of x0, so this is 0 plus 4 times f of x1, and f of x1 is 0.4, so 4 times 0.4, and so on until the very end, where you get 4 times x of x9, which is 1.1, plus f of x10, which is 0, and that gives you a total number of 41.87. Remember, the 41.7 is not your final answer, because the blood flow, or the flow, is amount of dye time over your integral, so C of t dt. And since we were given 5 as our A originally, and then we have our integral equals 41.87, you get 1.01 liters per second, and then you can 0.12 liters per second, and you can manipulate that in any way, shape that you would like. Alright, so the last part of this video is demonstrating number 16 on page 480 in our textbook, section 6.7. The problem reads as High blood pressure results from constriction of arteries. To maintain a normal flow rate or flux, the heart rate has to pump harder, thus increasing the blood pressure. Use Poiseuille's law to show that if RO and PO are normal values of the radius and the pressure in an artery, and the constrictive values of R and P, then for the flux to remain constant, P and R are related by the equation number 1 that you can see right there. So the first step of this problem is demonstrating that Poiseuille's law can give us this, oops, my bad, can give us this equation. So what I did here is I set up two equations that are identical, and what I'm going to do is, since we're doing a ratio, we'll have to put one over the other. And since we are looking for the pressure of P over PO equals RO over R to the power of 4, what we need to do is we need to solve for P in both of these equations. So what you need to do is rearrange. So you'll notice I already rearranged them, and what I did was I put my original pressure on the bottom and my P on the top, just like they did in their equation. So let's rearrange once again. So what I did was I acted like there was a big division sign here, put up both equations together. So what you can see is you can cross out most of the stuff, cross out your pi's as well, and then you end up with your RO. So what you end up with is RO or to the power of 4 over R to the, whoops, not that, R to the power of 4 equals P over PO. So this is just to show that a little algebra can go a long way, and some little rewriting can give us to the original equation that we were looking for. Part 2 of this problem states that we deduce that if the radius of an artery is reduced by 3/4 of its former value, then the pressure must be more than tripled. So what we need to do is verify that that number is actually accurate. So I'll pause this and write down a little bit of the equations. So you can see that I rewrote the equation that we got in part 1 as proof. I rewrote that here. And since our new R is 3/4 of R0, then I will put that here, and then I'll rewrite some more. So this is our new equation right here next to the star. So what we're looking for is P. So what we need to do is we need to rearrange the whole thing once again, some more algebra, and put this on the same side to give us P. So P will equal, all right, so when we rearrange everything, you get your pressure is equal to your original pressure times your RO to the power of 4 over 81 R naught to the power of 4 over 256. So what I did was my 3/4 R naught, I put that to the 4th power to give me this number. When I get to this step here, this second last step, I flip my 256 to the top, and I get 256 P naught R naught to the power of 4 over 81 R naught to the 4. So what we can cross out my R naughts, and magically my pressure is now 256 over 81 P naught, and if you do the mathematics for that, it is about 3.16 P naught. So your new pressure is now your new pressure is now 3.16 times the original pressure, just like the problem told us. So one of the main things to memorize here is that algebra goes a long way, and just never forget to rearrange everything, because sometimes there is no math needed, and the best way is just to rearrange everything.